Hello, welcome everyone. So, I hope you are enjoying the carbon-carbon bond formation reactions. It's amazing what this organometallic chemistry can do for these carbon-carbon bond formation reactions. We have seen the Suzuki reactions, okay, that is quite great. We have seen the Negishi reaction, we have seen also the Kumada coupling reaction. Today we will briefly discuss, each of these areas are quite huge and it has been studied over last few decades enormously. There is always a limitation of time how much we can discuss each of these reactions, but it is essential perhaps from the course perspective to discuss each of them briefly and try to convey the main messages that is there for these carbon-carbon coupling reactions, and then if time allows, maybe each of them we can come back separately and discuss in a greater detail. Today we would like to introduce two reactions, namely Sonogashira reactions and Heck reaction. In Sonogashira reaction, it's again a very powerful transformation where a terminal alkyne is reacted with organohalide, mainly aryl halide and vinyl halide. So, Sonogashira reactions are quite effective for such transformation and it has been quite widely used irrespective of industry and academia. Let us look at the Sonogashira reaction, the reaction mechanism, and what are the important features of this reaction that will be interesting from the course perspective. So, Sonogashira reaction. You are taking Rx, this R is aryl or vinyl, that is it, and you are having a terminal alkyne. Okay. So, this H is there. Overall you will get a palladium catalyst, usually nowadays lot of variations are there, copper 1 co-catalyst, okay, not cobalt, this is a co-catalyst, and a base which is usually stoichiometric amount, that is for example triethylamine and so on. Overall you get the product formation which is an internal alkyne. So, essentially from a terminal alkyne you get an internal alkyne in the process, and that is helped by the palladium catalyst. As you look at the reaction, you can imagine that palladium catalyst will undergo oxidative addition into this Rx bond, and subsequently this alkyne will interact. The way alkyne will interact is copper will be inserted into this copper acetylate intermediate will be forming, and then that will be transmetallating into the palladium. We will draw the mechanism and subsequently reductive elimination will be happening. So, what we will be discussing now is the reaction mechanism of this Sonogashira reaction. As we tell that it is a Rx, aryl halide or vinyl halide, it will undergo oxidative addition with metal, that means palladium, main involvement with palladium. After that acetylene unit, terminal acetylene unit or terminal alkyne has to interact with the palladium. The transmetallation will not happen directly, it will need the usually, nowadays various options are available, some traditional variation from these Sonogashira reactions are done, but usually what is happening is copper is helping in the transmetallation process. Overall, of course, you need a stoichiometric amount of base for deprotonation of the alkyne upon binding with copper, and subsequently it will be able to transmetallate, and in the final state we will see the reductive elimination between the R group of the Rx and the alkyne unit to give you the terminal alkyne to internal alkyne product. Let us look at the mechanism, which should be simple at this point, since we were discussing these reactions, quite similar reactions previously. Reaction mechanism will involve again ligand palladium 0 complex. It will react with Rx, that is the step which is oxidative addition, and from there we have ligand palladium R and X intermediate. This is the oxidative addition intermediate. We will have from there the transmetallation. So, that is transmetallation, I think that is the main interesting aspect. We have copper acetyl intermediate, acetylate intermediate to give you overall copper X comes out, and in the regeneration stage we have a stoichiometric amount of base plus HC, the starting material, and over here we have HNR3X minus coming out. During the transmetallation step, of course, this is a palladium 2, during the transmetallation again it is the palladium 2 and acetyl intermediate is involved. So, palladium 0 oxidative addition intermediate interacts with Rx to give you the palladium 2 intermediate. Now, this copper acetyl exchanges with the X. So, acetyl intermediate goes out, the X gets associated with copper, copper X comes out. Now, which copper X then react with the starting copper X or the regenerated copper X, react with this amine and the acetylene or the terminal alkyne to give the copper acetyl intermediate. From there on, it is the simple reductive elimination. That is the product formation between this carbon center and that carbon center. This could be a sp2 sp carbon center usually, that will give you the desired internal alkyne that you are looking for. So, what we have seen so far is starting from, let us say, bromobenzene and a terminal alkyne, you will be getting aryl substituted internal alkyne. So, if you are taking phenylacetylene and aryl bromide, you will get aryl phenyl acetylene compound. Well, these are really amazing transformation and it works beautifully. The catalyst loading can be very low, and nowadays different variation of palladium free, copper free, Sonogashira, all those different variation of the Sonogashira reactions are also available, but reaction works best when it is used in conjunction, in combination. That means both palladium and copper are used together. Okay. And these palladium and copper can be used in catalytic amount, but you need stoichiometric amount of base, because the deprotonation of phenylacetylene requires the base. Okay. Let us look at how this deprotonation will be happening during these processes. So, transmetallation is one of the most interesting step. Let us look at. So, you start with copper X, okay, and then react with acetylene, terminal acetylene or terminal alkyne, and overall you have first step as alkyne interacting with copper X. Now, itself this deprotonation will not be possible, deprotonation from here will not be possible, it is required to have the copper interaction, and therefore, it is now acidic enough for triethylamine to deprotonate. So, without copper, this deprotonation just by amine will not be possible. Once it is interacting with copper, then the pKa value goes down, the lower pKa value ensures that it can now be abstracted, this proton can be abstracted by this amine. In the process you have copper acetylene intermediate formation, and you get HNR3X, right, HNR3X you overall get from this process. Now, this is very simple. So, the role of copper we do understand now. The copper role is mainly in the transmetallation step, and the role of palladium is also very simple. It holds the catalytic cycle together. It gives the oxidative addition, then transmetallation at the palladium center, and then reductive elimination happen to give the product. It is a very simple and clean and efficient method. How efficient it is? Well, you can see it if you have two halide in one substrate, let us say alkynyl halide, you are reacting with one equivalent of aryl halide. Selectively only one halide can be displaced. So, one type of aryl you can introduce in one end, and on the other end you can introduce another one. On the, let us say you have divinyl halide and you try to react it with two different alkyne, you would be able to do that. Let us look at one such example where this reaction is facile and one can do this reaction quite efficiently, these Sonogashira reactions. Okay, the substrate we have in interest is a dichloride. Okay. The idea here is to put one alkyne here and a different alkyne here. Let us say you take one equivalent of this, and then one of the alkyne, let us say N-pentenyl alkyne, you take one equivalent and you are doing palladium catalyst, and you are taking a base, you are taking also copper catalyst. That is the first step. Second step, same pot you can take another alkyne, okay, and then you of course heat overall. Overall what you will see, this is one equivalent, this is one equivalent, and this is also one equivalent. So, one equivalent will react with this one first to give the alkyne in one end, the other end will not be reacting at all, that one will react with this one to give asymmetric or to differentially substituted alkyne into that olefin starting material. So, in one hand for one equivalent alkyne it will be this, and the other equivalent will give rise to the SiMe3 product on the other hand. So, what we are trying to tell them is, if we have multiple halide into your electrophile, each of those halide can be selectively reacted, because the reactivity of the primary one or the first one is much more compared to the one that is undergoing the product formation. So, we can selectively control the product formation very efficiently, and therefore, if you have alkynyl dihalide, each of those halide can be selectively transformed to the alkyne with the alkyne product to give the two differentially substituted alkyne into the final product. Therefore, let us look at once again, you have alkyl dihalide, the intermediate that is involved in this case is this one, in pentyl, let us say. Now, oxidative addition into this compound is faster, this is faster compared to this one. Okay. Therefore, you will get, if you take one equivalent, you will get the nearly 100% conversion for this product, and subsequently this chloride will react with that one. So, oxidative addition is fast in this substrate compared to that one, and that would lead to the product formation cleanly and in quite good yield. In the next part, we are not going to discuss way too many examples. One can take any number of examples and discuss the efficiency and everything. What in the Sonogashira coupling reaction we tried to discuss simply is, we need a palladium catalyst, we need a copper catalyst, we need a base, we need two coupling partner, one is halide electrophile. It could be aryl halide, it could be alkynyl halide. The other coupling partner that we need is the alkyne, that has to be terminal alkyne. Now that terminal alkyne CH bond will be displaced by this aryl halide aryl partner or alkynyl halide alkene partner. That is the Sonogashira reaction. Palladium will help us in doing the oxidative addition into the electrophile, and the copper will help us deprotonate the alkyne, and subsequently it will undergo the transmetallation step with the palladium, and then the reductive elimination will give the product. It is a beautiful reaction. Nowadays various variation is available, but overall what we see that we can control the substitution very efficiently, as we have seen with one example where two halides are there, selectively one halide at a time can be alkynylated and the other halide can be remain intact, and that halide can be again substituted by yet another alkyne to give the dialkyne substituted olefin intermediate. Now we would like to discuss another carbon-carbon bond formation reaction, which is again quite popular. As you know, Suzuki and Heck both shared the Nobel Prize along with the third partner. Now this Suzuki reaction we have seen, that is a Nobel reaction, and Heck reaction now we will discuss. Surprisingly, at the beginning when Heck was discovering the Heck reaction, he did not get enough support from the funding agency. I mean, can you imagine that? He has to, he has to quit from academics almost to do his chemistry. Heck reaction, Richard Heck was quite convinced that this is a great reaction, but funding agency could not believe or did not believe him that it was a important enough reaction. Well, there was a severe problem in funding, but as you know, since then like 70s, 80s, he kept on working on these reactions, and it becomes quite popular over the years, and subsequently in 2010 he got the Nobel Prize. That is quite amazing. Well, another sad thing is he passed away very recently, after developing this carbon-carbon bond formation to quite a great extent. So today we will discuss the Heck reaction, okay, and that is a reaction between aryl halide and olefin. Previous reaction what we have seen? We have seen aryl halide and alkene, or sorry, alkyne, terminal alkyne. Now we will see aryl halide and olefin. That is the main part of the Heck reaction. Now the various development has been done. We will slowly look at that, but mainly the Heck reaction as it is, that was what was discovered, and then how it was developed subsequently we will now discuss. So Heck reaction. Okay. Now the major part of the Heck reaction is Rx. This could be aryl and vinyl, or alkyl actually does not work, and it reacts with an olefin to give you the desired internal olefin, or the olefin. Usually it is an internal olefin that people are interested or people do get. So you need base in stoichiometric equivalent. All that is a quite interesting reaction in its own right. What we do see here is aryl halide, as you can imagine, it will undergo oxidative addition with palladium, and then olefin will coordinate beta migratory insertion into the olefin, and then beta hydride elimination from the product, from the from the product that is formed after beta migration. Subsequently, you will see the olefin is removed from the palladium. So, overall in this reaction we will see palladium will oxidatively add to halide, aryl halide or alkynyl halide. After oxidative addition, we will see olefin will coordinate with the metal center. From there on, insertion of the aryl or alkynyl part into olefin will occur, that is the beta migratory insertion. From that intermediate, we will see a beta hydride elimination to give you the, that is the thermodynamically stable product usually, to give you the olefin, the final olefin. So, you start with the olefin, you end up with another olefin where your aryl or vinyl partner is incorporated into the process. Into the Sonogashira reaction, you start with an alkyne, terminal alkyne, and the terminal CH bond is substituted by aryl or vinyl, which is coming from the aryl halide or vinyl halide. So, terminal alkyne to internal alkyne you form in case of the Sonogashira reaction. In case of Heck reaction, you start with one olefin, you get with a more substituted olefin, and both the reactions, as you can see, are quite important for synthetic chemistry. Let us look at the simple steps of the Heck reaction, what we try to discuss right now. So, Heck reaction intermediate and Heck reactions, the reaction pathway. Ligand palladium 0 that is crucial for the reaction. First step is oxidative addition, we will get Rx, and overall we will have palladium Rx intermediate, which is same as before. It will react with olefin, and from there on we have olefin coordination, just it is coordination, nothing else initially, and now we are ready for beta migratory insertion. Why it is a beta migratory insertion? In a moment we will see the palladium will coordinate with the carbon center, one of these two carbon center. With respect to that palladium carbon coordination, R is at the beta position. So, the intermediate we usually get is that one where we have R, this is the R, that is over this one, okay, or that is over that one. Now, it gets at alpha beta position, it gets inserted. So, this is the beta migratory insertion step. From there on, of course, you have to have after rotation, okay, after rotation after desired rotation where you will get to the right orientation. From here you will get beta hydride elimination to give the palladium olefin intermediate that is required for the product formation, and you have HX, both H and X can leave out, and the olefin is there that can again leave out from the product. Overall, in the final step you will have base coming out to give you BH minus BH plus X minus, and the product formation, that is R olefin R prime. Okay, that is the cycle we are drawing. So, it is a simple catalytic cycle that you have seen where palladium 0 oxidatively add to the aryl halide or olefin alkynyl halide, and subsequently what we do see is the olefin interaction with the palladium intermediate, incorporation of the R group coming from aryl halide or from alkynyl halide, that R inserts into the olefin at the beta position with respect to the palladium center where it is attached with the substrate, that center is beta, and from there on after suitable rotation what is required for the beta hydride elimination, we do see that it is the beta hydride elimination product gives you the olefin product which is coordinated with palladium along with hydride and X halide that is coordinated. If you give now a base will take up to give BHX intermediate, BH plus and X minus intermediate, overall you regain or regenerate the palladium palladium for the next catalytic cycle, and olefin also falls off from this intermediate. So, in this class so far we have seen two important reactions, Sonogashira and the Heck reaction. We did not discuss too much about the Heck geometry or the product geometry, where R group will be migrating, that aryl group, whether it will give you the 1,2 product or a 1,1 product. Those control of the geometry for the product formation we would like to discuss in the next class, and also we will be discussing in detail the selectivity that will be obtained during the product formation. Heck reaction could be little bit more interesting in terms of understanding how the product formation and the product distribution are happening. Not only that, this reaction we can have an asymmetric version. You are perhaps wondering how an asymmetric version can be introduced. We will be discussing that in the next class as well. You can do that. As you know, palladium can pretty much walk along the ring or along the carbon side. So, that could leave a option for the stereocenter generation. We will discuss about that. We will discuss some more example or the examples of the Heck reaction that we did not discuss too much today. In the next class then, I hope you will be able to remember this mechanism. Based on this, we will be able to discuss more of the examples of the Heck reaction and the asymmetric version. Well, till then, keep studying this Sonogashira and Heck reaction. We will come back soon with examples and discussion on the Heck reaction in the next class. Bye bye.